Kevlin, you have the screen. Thank you very much for being with us today.
Thank you very much, Alex. Right, okay, so for those of you who were in the room just before, the previous talk in this room was about nature and what we can learn from nature. What I'm going to do is I'm going to look at the other side of nature, if you like. I want to look at 6 impossible things. I want to look at things that are actually not possible, not ideas of inspiration, but where nature itself dictates boundaries to us. And this is important because I think sometimes when I talk about things that are impossible, people go, oh, right, yeah. In fact, I did it last week on Twitter. I was after some suggestions for ideas for that I can do in future. Perhaps I will do more impossible things in future. But a lot of people suggested things that were hard. That's not the same as impossible. If somebody says, oh yeah, you can't do that because it'll take 1,000 years. That's not impossible. You just told me what is possible. You told me it would take 1,000 years. That's a possibility. It's not very likely, but it's not impossible. I want to talk about impossible things that genuinely are impossible. So my name is Kevlin Henney. My job is to take you from the morning into the afternoon. And the quote of 6 impossible things comes originally from one of the Alice in Wonderland books from Lewis Carroll. It was from Through the Looking Glass. And it's the White Queen says, sometimes I believed as many as 6 impossible things before breakfast. This is in response to Alice saying, but you can't believe impossible things. And this is the whole challenge. So let's start off. We'll do it as a countdown. Okay. So please post questions as we go. I've got my eye on the chat. And if I see them, I will answer them. Otherwise, we'll have a few minutes at the end where we can pick them. I can pick up the questions. So representations can be infinite. Now, that's kind of an interesting one because infinity has a very peculiar place in mathematics, even in physics. It also has an interesting place in code. So I want to start off with a blog that I just published this week where I make a point. I say there are no infinities in the physical universe. Infinity is a mathematical concept, not a physical one. And this is quite an important idea because we use the term infinity very, very loosely. And we say, oh, yeah, sure, you can have infinities. Yeah, there are things that are infinite. No, you can't have infinite. The universe has not existed for an infinite amount of time. There is not an infinite amount of space. It is all finite. There are no infinities. But you say, yeah, but look, if I use a floating point number, then, here, I've got a representation for infinity and for minus infinity. It's like, yeah, but you haven't, that's not actually infinite. All we've just done is encoded the name infinity into a bitwise representation. That itself is not infinite. It's because we can't have infinity that we have to do this. And we also, in other words, we are able to encode something that implies infinity or suggests infinity, but it's of itself, it's not infinite. And we also have encoded the idea that there are other things that are not finite, things that are absent in a particular way. NaN being the most popular. In fact, yes, it is the most popular. We have JavaScript to thank for that. And I love this dialog box from Lufthansa, trying to parse NaN, but it is not a number. Of course, it's how very beautifully self-referential. But the idea of things that are not finite, having consequences in our code is important because we assume that, and this ties into something else, that everything has an answer. So 2020, there was this little headline: driverless race car drives straight into a wall. During the initialization lap, so this is a car race, something happened which apparently caused the steering control signal to go to NaN, and subsequently the steering locked to the maximum value to the right. I remember when I retweeted this that somebody said, oh, wait a minute, are you saying that people are using JavaScript in driverless cars? It's like, no, it's not. JavaScript is not to blame for NaNs. It's perhaps to blame for popularizing them, but NaNs are, and likewise, infinity representations are encoded in IEEE 754 and IEEE 854 standards for floating point representation, and that dates back to the 1980s. It's just that JavaScript, because it doesn't have a very good type system, I'm sure I'm going to get hell for that, but hey, it doesn't, honestly. Any language that uses floating point as its default number type, in fact, for most of its history, it's only number type, has problems and has created this situation where we've ended up with stuff that should have been handled in different ways because people assume that numbers behave as numbers do when you're at school, and they don't. And we end up with nans and imps and all kinds of stuff. In fact, the code, I believe, was used, I think it used, it wasn't Mathematica, it was another MATLAB. It used MATLAB. I knew it was one of the mathematical ones. So it used MATLAB. But there's another point about these numbers. There's another thing here. How many numbers exist? How many real numbers exist between 0 and 1? It's an infinite number. In fact, it's uncountably infinite. But therefore, we always have to approximate. And we use floating point numbers. Floating point numbers aren't real. As Chuck Allison. So a few years ago, I edited this book, 97 Things Every Programmer Should Know. And funnily enough, the idea that inspired the whole book was this issue that somebody had not understood floating point numbers, but had used them and come across an error. And I remember just thinking, oh, damn it, this is just something every programmer should know. And I suddenly thought, wait a minute, there's something here. There's a book. So I got Chuck Allison, who he's a professor of computer science. I've known Chuck a few years. I got him to write a piece. I gave him the title. Most people just submitted what they wanted, but I got Chuck because I knew he did floating point representation really well. I got him to talk about this, and he had this lovely way of describing it. Real numbers have infinite precision and are therefore continuous and non-lossy. Floating point numbers have limited precision, so they are finite and they resemble badly behaved integers. I think that's a lovely way of putting it. They are badly behaved integers. But even integers are not that well behaved. So, you know, here, if I go back a few years, Visual Studio is telling me that my license will expire to what most people will seem like an arbitrary number. But if you're a software developer, you're looking at that going like, well, hang on, that's 2 to the 31 minus 1. That's the maximum value of a signed 32-bit integer. It's just like, that's a bit suspicious. That's not an arbitrary number. Of all the 4 billion integers available within that restricted native type, this is a very suspicious one. It's the maximum value. But what I also like is that somewhere the comparison logic, there's clearly a difference here. It's telling me my license will expire after the human race is long gone. But apparently my license has gone stale. So in other words, there's a difference between what we're being shown and what we've got there. My license has gone stale. So this must have ultimately been a negative number here, and something has happened in the presentation logic that messes it up. And this is an important idea. This idea that things are bounded. We do not have infinities. Integers themselves are, in fact, this is one of the few justifications I can ever think. You know, if you ever had an experience using or learning Pascal or any of the related languages, in those languages, integers are called integer, and floating point numbers are called real. But they're not real. We've established that. And I quite like the fact that in Java and other languages, we tend to use int, and that actually comes from the language Algol 68 as the first to properly abbreviate it, int. I like the use of int rather than integer. Why? Because it's not an integer. It's a truncated version of an integer. There's a limited number. And this can catch us out because we are often given the illusion that it doesn't matter, and most of the time it doesn't. So let me take you back to 1983. And in fact, you can find this paper. This was actually John Bentley's Programming Pearls column in Communications of the ACM, which was collected into a number of books. And this particular one can be found in Programming Pearls by John Bentley. There is a second edition. It's not in that one. And there is also a more Programming Pearls. But you can find this particular piece. It's entitled Writing Correct Programs. And this is unfortunately a little bit ironic. He wanted to show how to write correct code. And he demonstrated this with a binary search algorithm. Okay, and this is actually slightly different the way most people have written binary searches. And so he shows a very effective way of doing this. He's just got pseudocode here, but then he expands it out. So this is the basis of the binary search algorithm. He then expands it out with all those extra things, those things that say must be and they're in curly brackets, those are basically assertions. Must be is another way of saying assert, or this must be true at this point. And so he is using a kind of a form of formal verification. And he's trying to make a case of formal verification. And he says one of the major benefits of program verification is that it gives programs a language in which they can express that understanding. And so we should always be aware and keen to extend our toolkit, our mental toolkit and our vocabulary toolkit, to be able to talk about the things that we build. Software development is ultimately very abstract. So the more ways we have of approaching the abstract, ultimately the better it will be. But these are, as he points out, he does acknowledge these techniques are only a small part of writing correct programs. In fact, these days, formal methods never became a thing. This was in the early 80s. People thought formal methods would become a mainstream thing. Formal methods have found a place, and formal proofs are useful in certain contexts, but normally they are behind the tools that we use rather than in the application software that we use, and they are often used in very restricted environments. And there, for example, we might find a particular use in concurrent and distributed environments for proving that certain states can and cannot exist. But we also know that there are many other formalisms, and we have other checking tools available to us, and we're also probably better at tests than we are at formal verification. But he does point out, keeping the code simple is usually the key to correctness. Yes, in other words, there's more ways to arrive at this destination, but having at least semi-formal reasoning can help us. But he then does highlight an issue. On the other hand, several professional programmers familiar with these techniques have related to me an experience too common in their own programming. The hard parts work the first time while the bugs are in the easy parts. I bet you have had this experience. I have had this. Sometimes you are so focused on getting the bit you know is hard right. You say, right, okay, I'll go. You got this. You've got all the thoughts in your head. Nobody disturb me because I think this is going to. You do that. You do the hard bit. The hard bit is good. You completely forget to update something else, or there's an off by one or a null pointer exception in some other part of code. You completely overlooked. It's in the easy part that you will find most of the bugs. It's to do with assumptions. Assumptions are blind spots. So what I'm going to show you here, this is code from the JDK from around 2006. This is binary search. It was implemented by Josh Block, who was a student of John Bentley's. And if you look closely, you will see the three-way partition that he uses is identical to what we showed in the pseudocode right here. Okay, it's exactly that. Okay, so Josh has taken this, and all is good, except for an assumption. What happens when you use very large arrays? Here's the assumption. Here, the midpoint. You know this with binary searches or various sorting algorithms. When you say you add the two that you're looking for the midpoint. Okay, I've got two things. I'm looking with binary search. You're chopping down in halving, so you need to find the midpoint of things. And this is the way you would do this if you were a mathematician. And importantly, this is the way people default to think of it. I add the two things together, divide by 2. It is the mean. It is the arithmetic mean. It is the average of the two position. That is what the midpoint is. There is only one small problem. Integers are not integers. So although Bentley proved his code was correct, he proved it in the presence of infinite integers. Unbounded integers, integers that are countably infinite. There's a problem with this. It doesn't work. If low and high are really large numbers, you add the two together, they become a very negative number. They wrap around. The correct way to implement this, and also perhaps the most efficient way as well, is what you do is you take the low point, you find the average distance. In other words, you basically take the distance and you halve it between those, which is, from a mathematical point of view, equivalent. But that's the point. We are not dealing with mathematics. This is the assumption here that integer division at this point will work. Now, as I said, assumptions are interesting pieces of knowledge. They are a blind spot. From a point of view of epistemology, in other words, the philosophy of knowledge, assumptions are like trying to tread across a room with Lego bricks, but the room is dark. You might know that you have assumptions. You might know that there are Lego bricks there. The problem is you don't know where they are until you step on them. Assumptions are normally only discovered when they are broken or stepped on. That's why I say they're very interesting pieces of knowledge. You normally only go, oh, I had assumed that, when your assumption is contradicted. So we find all of these issues here, and they plagued us for many years. Back in 1998, this is the USS Yorktown, which has since been decommissioned. It's a cruiser, and it was put out of action for a whole weekend by the installation of Windows. They previously used a version of Unix, and the source of the problem on the Yorktown. So basically, the whole system shut down. The data contained a 0 where it shouldn't have. When the software attempted to divide by 0, a buffer overrun occurred, crashing the entire network and causing the ship to lose control of its propulsion system. Now, I'm going to say that this is, although there's not a lot of detail on this, I'm going to say this is not actually a Windows problem. This is most likely a driver problem. The Windows kernel protects against this kind of stuff. What is most likely the case is that there was a driver that was added, a network driver, and it is the driver that did not protect against this. You can't have infinities, okay? Shakespeare noted this. He said, this is the monstrosity in love, that the will is infinite and the execution is confined. The desire is boundless, but the act is a slave to limit. We are in the confined space of execution. We are slaves to the limits of physical hardware. Now, something else that is universal that we need to understand. This is not possible. We have the idea that every question has an answer. I can offer a query so I can have an answer. Not every question has an answer that is in the expected form. So this is one I use quite a bit. Yeah, Facebook, there was some kind of bug. I submitted feedback on this. Your Facebook will be used to improve feedback from Facebook. Thanks for taking the time to make a report. How much time? Well, my reply apparently was logged as 31st of December, 1969. It's like, oh, okay. That's a bit of time travel, unexpected time travel. So what have we got here? What's the interesting challenge? I mean, why 31st of December 1969? Well, 1969, 31st of December, that seems really close to, yeah. Well, to understand this, we need to understand that no matter what layer of abstraction you think you are working at, always remember that there is stuff further down that leaks through. We had this with the Spectrum bug a couple of years ago. Turns out that JavaScript is susceptible to basically caching, processor caching issues. Most things somewhere in their stack are implemented in C. So this is one of those things. People often use this phrase full stack developer. I will confess I'm not a full stack developer. If you don't know C, you are not a full stack developer. Full stack developer is basically, I'm a JavaScript programmer. That's what it's short for. I do front end and I talk to the database. That's a tiny piece of the stack. It's a tiny, tiny piece of the stack. That's not even the bit of the stack that I used to, my background is in systems programming and real-time programming. My stack starts below that. But the stack also includes the laws of physics and the universe. It also includes C. The time function shall return the value of time in seconds since the epoch. This is the POSIX standard. The time function used in C and therefore exists as the default way of accessing time on most systems at the lowest level. And what is epoch? Well, you can actually find that out through a number of other errors. Here's another error that, if you didn't already know, I collect error screens. Here's an interesting update for Intel drivers. I don't think Intel were distributing drivers on the internet on the 1st of January 1970. But you will notice here, this is the epoch. This is time 0. Time 0, 1st of January at midnight, okay, the beginning of the day. And now you suddenly realize, wait a minute, that's just after 31st of December 1969. My original thought on this was that there was a time zone shift. I'm based in the UK. Facebook is based in the US, and therefore it is west or negative time-wise from where I am. So I assume this was a time zone adjustment initially. But later reflection made me come back and think, actually, that most likely wasn't a time zone adjustment. If we look at the C standard in detail, and I have a copy of the 1989 standard, it's not light. So if we look at the C standard in detail, what it tells you is that -1 is returned if the calendar time is not available. Now, what I think is interesting here is that for many people, they go, well, wait a minute, how can the time not be available? And this is the assumption that they had. I think we're all familiar with the idea that not every method can succeed. The idea that we might go, oh yeah, of course, you can call a method and it throws an exception, or you can call it, it returns a failure status. Although clearly here, returning a failure status that is also a valid time is probably not the best piece of design. But then again, strictly speaking, you're not allowed to go back before the 1st of January 1970. So it's not strictly speaking a time. But the fact that a lot of systems implement that and allow you to have negative time, but also have -1 as an error indicator, there are questions of language design here, but that doesn't remove from the idea that this is a failure mode. And it's an unexpected failure mode. Because many people say, if you said, are you expecting, you're going to query the database, is that call going to work? You go, well, no, what if the network's down? You would expect an exception. But when you ask for the time, people often believe, oh yes, of course I know the time. The time is freely available. It is everywhere. It's universal. No, it's not. Actually, it's not. Where I'm sitting in my office, I can see 4 different devices that give me the time. And they agree within about 1 minute of each other, which probably means my office is 1 light minute across. But the point is, I have 4 sources of time. I could have 0. And we must also remember that time is a service provided by the operating system. It is outside your control. You can ask for time and not receive it. This is the assumption that people forget, that time is not a guaranteed. You are not guaranteed to have that available like any other service. And so therefore, the answer to what is the time is actually not a time. I don't have that. That is not available. It's not actually a value. Not every question has an answer. So let's look at something else. Let's look at the kind of comfort zone of computer science, algorithms. What is an algorithm? It's a process or set of rules to be followed in calculations or other problem-solving operations, especially by a computer. Okay, that's what my dictionary tells me. And let me give you a terrible, and given that people who have done computer science degrees are normally subjected to this, various sorting algorithms. Let me give you a terrible sorting algorithm. Over the last few months, I've been writing a few blogs going deep diving into what are known as esoteric sorting algorithms. I've done sleep sort, drop sort, and here is my piece on permutation sort. Permutation sort has a terrible complexity. It is factorial. It is honestly quite terrible. The performance is shocking. Just sorting 10 items takes you to 3 million potential for 3 million exchanges and comparisons. It is a systematic but unoptimized search through all the possible permutations of the sorted arrangement of things. Now, let's do this in Groovy. I need to have a predicate, a function that defines what it means to be sorted. So this is what it means for a list to be sorted. And then I can define permutation sort. There's a permutation generator that I can use. I've made sure that we capture the empty case. It is perfectly legal. For some reason, permutation generator makes a mistake on this. And I am going to say it's a design error because the permutation of an empty list is perfectly well defined to be an empty list. But I've accounted for that case. And here is permutation sort. It is really bad at performance. This is an algorithm. Here's the challenge. Surely there can be nothing worse than permutation sort in terms of performance. Don't be so sure. I published a piece on BOGO sort at the beginning of this week. The essence of BOGO sort is to shuffle values randomly until they are sorted. Not systematically, but randomly. We may encounter the same permutation twice. Here's a very simple implementation of BOGO sort in Groovy. It's actually a little bit, it's accidentally optimized. In fact, I found this error exists in most versions of BOGO sort that I see online. People do, while it's not sorted, then shuffle the values. If it's already sorted, then this is optimal. So we need to sub-optimize it. There we go. Always shuffle and then check sort. So shuffle first and then check. Now, of course, there is a point here. This is terrible performance. But you might say, yeah, but we're using, isn't that an artifact of the fact that we're using, there's potentially a case that we're not really using real random numbers. It's like, actually, it doesn't make any difference. But of course, we do need to acknowledge that, as John von Neumann observed, anyone who considers our arithmetical methods of producing random numbers is of course, in a state of sin. It doesn't make any difference to use true random numbers, which we can get from secure random. We can adjust our shuffling to take advantage of secure random, which will use a truly random seed, and that truly random seed will, depending on the platform that you're on, will be taken based on the entropy of something that is read typically from the processor. Now, we've addressed that issue. We've got pseudo-random numbers and random numbers. They both have terrible performance. But the challenge here is it an algorithm? Well, what is an algorithm? An algorithm is a specific procedure for solving a well-defined computational problem. Yeah, it's not specific. It's the first observation. We're using random. We're using random numbers, so therefore it's not specific. But actually, there's another challenge. There is a distinction in computer science normally that we don't need to worry about. But a procedure which always terminates is called an algorithm. Okay, therefore, an algorithm by definition is something that terminates. It has a result. Bogo sort is actually not an algorithm because it's not guaranteed to terminate, which leads to a rather interesting question. How do we test it? So this is a kind of classic book, which I do actually have. I quite like. I like the history of programming, and so I collect old books. Structural programming. This is from 1972. Let's check this out. This is kind of 1972. So 50 years old this year. There's a lot of good advice here, but also it's very historical in other sense. There's a lot of interesting stuff. There's you can find object-oriented programming. Yes, object-oriented programming is a form of structured programming. Who knew? Well, of course, it's structure. There's a lot of things that people talk about structured programming that are, if they actually read the original book, would be they'd probably think differently. But this is the source of the famous Dijkstra quote. Program testing can be used to show the presence of bugs, but never to show their absence. How do I demonstrate that Bogo sort works? Well, here we have a function, a test function. So just using JUnit4 binding to Groovy, I've got some values 314159, and I'm expecting 113459. I Bogo sort these, and I'm asserting that values equals expected. You know what? Every time I run this, it's going to succeed because the probability that it doesn't terminate is absolutely minimal. But I mean, so small that a floating point number could not represent it. That's how small it is. How do I assert that it terminates? I would like to assert that this actually terminates. Well, the only way you can do this is to add a timeout to the test. And basically, if you reach the end of time, then it did not terminate, and therefore the test will fail. You might notice that there's a small problem with this. And it's not just that JUnit doesn't have an end of time constant, it can't. That doesn't mean anything. There is no way you could ever run this test. The universe there is no such thing as infinity. We cannot reach the end of time and then do something. That does not have any meaning. The universe is bounded by physics and our patience. We will not wait that long. But that also gives us an understanding. It gives us an understanding that the behavior that we are testing is not unit testable, because outcome is not uniquely defined by the correctness of the code. It's defined by external factors. And testing the correctness of this is like testing the correctness of an interaction with a database. It's effectively an integration test. Therefore, we will add a timeout that is more reasonable. And that's actually, so in other words, let me give it a second. For this, actually, it always runs within a second, and that's fine. The point here is that this is how you can actually address something that is far deeper, known as the halting problem. About whether we can write an algorithm to determine whether or not something will terminate. Alan Turing demonstrated in 1936 that actually no, you can't. That there are things that will run forever, and you cannot determine in advance automatically whether they will run forever. But we fix that. It means we can actually address the halting problem. What you do is you recognize this from loads of code. Whenever we are dealing with indeterminacy in time, what we do is we change it to indeterminacy in result. What we do is we say you either have a result or you have a failure at a particular point. You are guaranteed time-based behavior, but you're not guaranteed which of these two options you're going to get. But I can tell you, it will never take longer than 1 second to execute. You either achieve failure or a value. So what we do is that, because what we do is we give up asking, there is no answer to the question, does the test pass or fail? In some cases, there is no answer to that question. What we do is we make an answer. We say, we didn't find out and we gave up. Now, in this vein of philosophical thinking, every truth can be established where it applies. That is one of the impossible things. You cannot establish everything that you need to know at the point at which you need to know it. And where does this come from? This kind of comes from Kurt Gödel, Gödel's incompleteness theorems. There's a nice piece here on Adrian Collier talking about measuring fairness in machine learning algorithms. He points out this is the kind of the grand vision, and just to take you back to the turn of the last century. In the 1900s, there was this vision that physics and maths were almost done. We are finished. We've learned everything there is to know. And that maths could be demonstrated to be complete and consistent. And that was one of the challenges, one of Hilbert's challenges. And meeting this, Bertrand Russell and Alfred North Whitehead published Principia Mathematica in 1911. Basically a proof that mathematics was logical, complete, consistent, and everything. 20 years later, Kurt Gödel kind of basically shattered the dream, showing for any consistent axiomatic system, there will always be theorems that cannot be proven within the system. So this wonderful book, Gödel, Escher, Bach, really explores a number of things to do with human intelligence, to do with the universe, to do with mathematics, computability, and so on. And summarizes it as like this: all consistent axiomatic formulations of number theory include undecidable propositions. You go, well, yeah, Kevlin, but we're here to talk about code. Guess what? Code is can be demonstrated to be equivalent to a formulation of number theory, which means that code contains undecidable propositions. Now, there are a number of different ways of establishing this, but I'm going to just look at a very simple one. How long is a piece of string? So let's switch to C for a moment. And you might say, well, hang on, you know, I'm a JVM kind of person. Why should I care about this? I'll let you know in a minute. But first of all, it's easiest to demonstrate this in C. I can do it in other languages, but it requires a bit more setup. What we're going to do is going to find the length of a string. Standard function striln, okay? Because back in the 1970s, there was a shortage of vowels. You couldn't use full words, and and this inhibited a lot of things. But from the 1990s onward, we discovered a new supply of letters, and these have all been made available. So this is string length. Size T is an unsigned type that is used to refer to the size of types. Great. Const char star s, that's a string. Basically, we have a pointer to the beginning of a sequence of characters. Okay, what defines the end of a string in C is the null character. Okay, so we've got the pointer to the beginning and we can traverse that. Okay, and we can treat that like an array. So what we're going to do is we're going to basically count up the number of characters until we hit null. What could be easier? We start off, n is going to be 0. So I'm actually using an implementation that's very similar to the implementation you'll find in the original C programming language K&R books. While n from the beginning of S does not equal the null character, increment n, and then return n. Kind of, we're done. Okay, so now comes the interesting bit. What must be true for us to succeed in this? Well, the first thing is S is a pointer. It must not be null. I can assert that. That's within my scope. But is that enough? Does that guarantee that we will basically, this is related to the halting problem and to other such things. They all came around, by the way, at the same time. We need this as well. Now, I put this in gray. If you look at it closely, you'll also start recognizing why, because I've gone and used a whole load of extra notation that comes to us from maths, but it's not present in C. What I'm asserting is that there is an n, there is a position where there is a null, and that all of the positions between the beginning of the array and the where that null occurs are actually valid. In other words, you haven't wandered off the end of the array into some other part of memory. Technically, these in C are known as undefined. So there is an interesting question here, is that this is the precondition. And what is interesting is it cannot be asserted on because it can't even be written. Within the system of Strelen, within the axiomatic system of this function, it is not possible to prove that S is able to meet the preconditions that would guarantee its postcondition. It's not possible to do this by proof. The only way you can do this is by going outside and seeing how it's called. And that was the whole point with what Gödel was saying, is basically we can't prove that this is correct. There are things that are true that cannot be proven to be true at this level. You have to go out to the next level and look at the calling context. And you have to go out to the next level beyond that to prove things about that. In other words, there are statements that are true but cannot be proven to be true in that context. So if we jump outside, let me show you an example. I've got a string here, be excellent to each other, and I can print out Strelen, and there is a null automatically. The C compiler inserts a null at the end of this. This is well defined, and this will give me the answer, be excellent to each other, 26. But here we have another problem. What I've got here is I'm going to allocate only 5 characters, BOGUS. In fact, the compiler will allow me to do that. It will actually allow me to write that, but it won't insert the null because it's not allowed to. There are only 5 characters. This does not have null termination. Now, what's actually going to happen when you run this? Well, you know what? Sometimes you're going to get that because the way the compiler allocates the space is you end up with that. But it's not defined to have that. You have no guarantee. This is just as equally likely. You could end up in the void. You could end up heading towards the galaxy M87. The point there is that from the outside, this is statically checkable. Inside Strelen, it's not checkable. So basically, this is a very simple demonstration that we cannot prove inside Strelen that Strelen has been called correctly. Likewise, if I do not initialize, well, the joys of unmanaged languages and old school languages, if we do not initialize this, this is a garbage value, and boom, bang, there you are in M87. You know, this is not defined. Now, let me come back to something about why this is relevant. If you're thinking, oh, good heavens, thank goodness I'm never going to have to deal with Gödel's incompleteness theorem as well. Most people don't think of it like that. And you might say, yeah, I'm working in the Java space. So during early lockdown, Trisha G and I finished editing 97 Things Every Java Programmer Should Know. And actually, there are a number of speakers here, Josh Long, Adam Bean, Edson Yanaga, who actually contributed to this book. But the one I want to focus on is this piece by Thomas Ronson, How to Crash Your JVM. It's something Thomas and I had discussed a number of times. It's like his whole, I love this whole point he was trying to make. It's like, how many ways can you crash your JVM? Because everybody thinks, oh yeah, I'm in Java, I'm working in a safe space, you know, and therefore I don't need to worry about the world outside. And the point is you do, because your program exists in a context. It exists on an operating system. It exists in a universe that has boundaries. It exists in systems that have networks. But more importantly, one of the simplest ways we need to recognize is that C stuff is, how do I introduce undefined behavior in a language that is otherwise incredibly well defined? You write some native code. All the syntax of C, all the safety of C. But there are other implications about what we've just described here. As Adrian went on to talk about, one premise of many models of fairness in machine learning is you can measure the fairness of a machine learning model from within the system, from the properties of the model itself and perhaps the data it is trained on. What Gödel teaches us is that a machine learning system, to be demonstrated as fair, you need information from outside the system. So there's a deeper point here than just about whether or not you're writing well-defined C code. It's a much deeper observation. And that objection can be raised about many of the ways that we casually talk about the architectures of web-based systems. So in 2020, again, in our first wave of lockdowns, a performance artist, Simon Weckert, in Berlin, he demonstrated something rather fascinating. And what you're looking at there is a cart with lots of Android phones. This is what he did. He walked around the streets of Berlin with smartphones, all Android, and created traffic jams. Because this is important. How does Google Maps know where there is a traffic jam? The answer is it doesn't. And it cannot know that there is a traffic jam, given its current technology and the way that it's defined. unless there is somebody there looking at something that says, yes, this is a traffic jam, unless you have another separate piece of software that is actually analyzing the image of the street in real time in a way that is guaranteed, you cannot know that there is a traffic jam there. What you can know is things that typically correlate. And what the problem here is that we kind of confuse one thing for the other. We are assuming that 99 smartphones moving slowly is the indication of a traffic jam. It's not. It's 99 smartphones moving slowly. The probability that it's a traffic jam is high, but don't confuse one thing for the other. People do this all the time. We see it in metrics of engagement. There are whole marketing departments dedicated to engagement. This is absolute nonsense. It's statistically and scientifically invalid. The problem is that most people who deal with marketing and business do not have a background in stats or science. Engagement has a very specific meaning. If you look it up in the dictionary, it's a state of being engaged. Is that what you're measuring? Are you measuring somebody's emotional involvement and commitment? You're not. You're looking for correlates, and maybe some of them are true, but it's statistical. What you're actually measuring is clicks and shares and the amount of time, not that somebody spends on a site. This is also important because I say, oh yeah, sometimes people say, well yeah, but you're seeing how much time somebody's spending on a site. No, you're not. You're not seeing how much that time that person is spending on the site. You're seeing how much time there is a window that it remains on that site, or a connection is not broken to that site. Yesterday was a good example. I was doing something, I was on a site, I received a delivery. Doorbell went, I got up. For 2 minutes, I was not on that site, but that 2 minutes is part of the statistics that is included. Apparently, I was much more interested in that site than actually I was. I came back and moved on to a different page. I really didn't want to spend more than 5 seconds there. But because I was interrupted, that's now 2 minutes and 5 seconds. So there's a lot of things that are being said that are absolute nonsense because they cannot be demonstrated at the point that we need that knowledge. We must be careful not to confuse the data with the abstractions we use to analyze them. You know, I'm not saying you can't make these statements, but always make sure you're making the right statement. You're not making statements about engagement. You're making statements about clicks and shares. You're not making statements about people. You're making statements about software. We don't measure people. We measure the software that they interact with, okay? And we try and guess what the people are thinking. Now, another one that, again, seems blindingly obvious. The future is knowable before it happens. Of course, this is impossible. But this actually relates to the way that we articulate and reason about knowledge. So the late, great Grace Hopper, basically one of the people who invented the compiler, and actually an incredibly wise individual in many, many ways, very insightful. I love one of her quotes. To me, programming is more than an important practical art. It is also a gigantic undertaking in the foundations of knowledge. For me, that characterizes what I care about and what I think about when I think about software. Is the idea of software development is about knowledge acquisition and knowledge communication and expression. We're trying to formalize a knowledge system. That's what a code base is. It's a codified knowledge system. Okay, it's not a production system, it's not a manufactured system. It is a system of knowledge and meaning, which means that we should actually pay more attention to what is knowable. And we can categorize and organize our knowledge into different levels or degrees. The known knowns, the things we know, the things we know we don't know, the known unknowns, the unknown unknowns, the things we don't know that we don't know. This is your assumptions. Until you step on that Lego brick, you didn't know that it was there. But what is of most interest here is the unknowable unknowns. The unknowable unknowns, in other words, I didn't even know. It's not just that I didn't even know that I didn't know something, is that I do not have a procedure to determine what that knowledge is. For example, a halting problem. But this also relates to, the techniques people use in their code. I love this quote from Seth Rosen, this tweet from last year. When people try and make things future-proof or easy to change and stuff like that, always be really careful with that. You're making predictions about the future. You're trying to basically say that you know stuff about the future. Do you? But this is a good joke. When naming things like tables, always future-proof. If you sell wine, calling a table wines will be confusing when you've expanded to beer. So beverages, but that will be confusing when you sell ice. Products, when you expand to services. Yeah, Therefore, we recommend that tables be called stuff or table one. And it's funny you mentioned that. I remember doing a code review a few years back and just looking at the title bar at the top of the screen, and I just said to the developer, wait a minute, this is all in a file called stuff. You know, so yeah, sometimes people do take that a little bit too literally. The observation we have is that prediction is very difficult, especially about the future. Now, what I like particularly about this quote is, I've got it there as Niels Bohr, but I've also put a question mark because I always used to quote it as Niels Bohr. My co-authors in one of the books that I wrote, they preferred referring to Yogi Berra. What is interesting is that having researched this and looked around a little more, we don't know who said this. This is fascinating because this is about the past. If prediction is difficult about the past, how on earth are we going to be able to do stuff about the future? And of course, this ties into things like estimates. So this one from Work Chronicles, what's the estimate? A month. What if we add one more engineer? Then 2 months. Okay. First of all, you had me on the second frame. Then there's a pause. If we had a project manager, trust me, you don't want to know. Let's talk about this. Let's talk about this question of future. Let's talk about the things that we cannot know. In other words, we do not have a process for finding them out. So there's this jargon term. We find it in business. I see it in software architecture, and when teams are talking, people often use the term roadmap. Now, I don't have a problem with the term roadmap. I just have a problem with people misusing the word. Because you can go online, and I did this last year. I sat down, I thought, right, okay, let's just go online and find all these roadmap. Let me find these roadmap templates that you can use for PowerPoint. There are loads. And you know what they all have in common? They all have one road. I mean, they often have a very visual, you know, hey, it's kind of cute. Our roadmap has a road. Yeah. And you put your text there and it shows you the progress. Yeah, that's fine. But here's a real roadmap. I'm based in Bristol in the UK. This is what Bristol looks like. You'll notice it's a little more complex. And although there are highlighted roads, there's more than one road. The point there is that the reason the roadmap metaphor is valuable is because if you do it right, you will include multiple roads. Because if you include one road, first of all, if I have only one road, I don't need a map. Really? You know, if you have one road, why would you need a map? That doesn't make much sense. But it also projects a different kind of confidence. Here's another one of those PowerPoint ones. This one I love because obviously this was like, they must have published this in 2018. But I want you to notice here, 2020, how many people had global pandemic destroys the way that we work forever? How many people had that in their plan, in their roadmap? Global pandemic disrupts the markets. Global pandemic disrupts our daily office work. Nobody had that in their plan. And importantly, nobody could have done that. It's not a piece of knowledge that you could have known until you arrived. So if your roadmap only has one road, then either you can predict the future, in which case, why are you still in software development? There are far more interesting things to do. Or it means that you've assumed that the future is knowable before you arrive there. We have another practice where people do this. I hear this a lot. People talk about prioritize by business value. We're going to prioritize our requirements by business value. There's only one problem. You can't do that. I'm not saying you shouldn't do that. Sometimes people misunderstand me, particularly in the agile space. Oh yeah, but you know, sometimes people tell me, oh, we do it all the time. No, you don't. You do not prioritize by business value because until the future arrives, you don't know the business value of that thing you've just developed. You cannot know unless. So in other words, prioritizing by business value is not about choice. It's about the fact that laws of physics prevent, to the best of our knowledge, travel into the future. The best you're ever going to do is prioritize by estimated business value. Now you might say, Kevin, you're just playing word games. You know, it's the same thing. No, it isn't. Trust me. If you are a software professional and you've not worked out that actual is different from estimated, then we need to have a conversation. An estimate is fundamentally different. If you do not know the business value, you can only estimate the business value. If you want to say prioritize by estimation, then that's fine. But remember, estimates are probability distributions. They are not finely ordered things. So back to Grace Hopper. The point is, yeah, I'm asking you to change the way that you work. Humans are allergic to change. They love to say, we've always done it this way. I try to fight that. That's why I have a clock on my wall that runs counterclockwise. And Grace Hopper is one of the reasons I have I have a clock on my wall that runs counterclockwise. And in fact, that's one of the time devices I was referring to earlier on. So 2 things to go. Second last one, a distributed system is knowable. Distributed systems challenge us in a number of different ways. Leslie Lamport's definition, still good to this day. A distributed system is one in which failure of a computer you didn't even know existed can render your own computer unusable. I had an example of this from my publisher O'Reilly a couple of years ago when there were forest fires in California. The point is that although we like the idea that cloud is, geographically location transparent, it's not. The cloud is very, very definitely bound by physics. It's bound by the location of data centers. It's bound by things like the speed of light and all kinds of stuff. There is a genuine difference. But there is something deeper going on here. And this is captured by Brewer's theorem, which many people better know as the CAP theorem. And it is a theorem. It was introduced kind of as a principle at the end of the 90s. Going into the 90s, we had the assumption, there were 10 assumptions from ANSA, ANSA, 10 assumptions you should never assume about a distributed system. In the mid-90s, there were 8 fallacies of distributed computing. These were related, and then we had this as a principle based on 3 things, and it was then demonstrated to be actually a theorem that was formally proven in 2002. And CAP stands for consistency, availability, and partition tolerance. Although I kind of wish that it had been called tolerance, and then we would have ended up with CAP theorem. But basically, the idea is that you cannot have more than 2 of these. Any 2, but you cannot have all 3. Partition tolerance, just in case you're not familiar with the term, partition tolerance basically means as if your network partitioned into 2. It's a polite way of saying message failure. What happens if not all the messages get through? And if we're talking about, this is from the point of view of data, consistency has a precise meaning. It means that whenever I request, every request for a piece of data gives me either an error or it gives me the most recent result, okay, the most recent update. Availability always gives me an answer, but it's not guaranteed to be the latest. Okay, and partition tolerance means that everything still works when you in the presence of failure, partial failure. So you can have consistency. In other words, I can guarantee you, I'll either, in the event of failure, I can guarantee either you're going to get the latest value or you're going to get an error, or I can guarantee you'll get a value, but I can't guarantee it's the latest. Now, sometimes people say, but this category, consistency and availability, but no, partition tolerance is not meaningful. Actually, it is. It's meaningful in the limit. If you are working within a single address space, then you're not subject to partition, and you don't have to be partition tolerant. You can guarantee consistency and availability because there will be no partitioning. If you like, the CAP theorem is kind of a Heisenberg's uncertainty principle for distributed computing. To quote Douglas Adams from Hitchhiker's Guide to the Galaxy, we demand rigidly defined areas of doubt and uncertainty, and that's what we have here. So this is important, though, to understand that that doesn't justify the errors that we sometimes see. I often see this, and I don't know whether this is as a result of the rise of kind of like micro front ends, but I often see cases where I'm looking at something and it says, you have 5 messages and it's showing me 4. Or no, even better, you have 4 messages and it's showing me 5. There's a technical term for this. It's called bad UI design. You can't blame it on eventual consistency. You're in the same process. Those are the same screen. They are running from the same executable process. They're in the same address space in most cases. But even so, they are on the same device. If you've ended up with inconsistencies like that, don't blame eventual consistency or distribution. Blame your architecture. That's a bug to be fixed. So the final one, technical debt is quantifiable as financial debt. Now, the observation that things get tough goes back to 1980. As an evolving program has continually changed, its complexity, reflecting deteriorating structure, increases and less work is done to maintain and reduce it. In fact, this goes back before that, but Meyer Manny Lehman articulated it best. Martin Fowler helped popularize technical debt, which dates back to actually 1992, but Martin Fowler in the 2000s really kind of helped move this forward. And he said technical debt is a wonderful metaphor developed by Ward Cunningham, so say coined it in 1992, or coined the concept of the debt metaphor. He didn't use the words technical debt, to help us think about this problem. Okay, like a financial debt, the technical debt incurs interest payments. Okay, this comes in the form of extra work and extra effort we have to do because of a particular design choice. But the thing we need to remind people is this: it's a metaphor. I often find myself cautioning against this. I find people treating it as if it's actually a financial debt. There are tools that will give you a financial value of the debt in your code base. This is just nonsense, because that's actually an unknowable value because it's based on a number of things that cannot be resolved. So it's wrong on two levels. One, it's not possible to know the financial equivalence of that. And the other is because that's actually not what the debt metaphor is about. Okay, so there is a fundamental issue here. A lot of people in their heads, when I say, oh, you can't estimate the technical debt on your code like this with numbers, the way that you've done it, I get people saying, oh yeah, we've estimated how much work it would take to fix. Well, first of all, let's be very clear. That's an estimate. That's not the actual debt. An estimate of a debt is not the same as the debt. The debt is the actual value. An estimate of the debt is different. We've estimated this in hours. How long would it take to fix the technical debt? But that's based on, and then how much is an hour worth? Again, there's some very funny economics going on there, but let's just say that that's possible. You haven't actually worked out the cost of the debt. You've worked out the cost of repaying the debt. That's not what technical debt is. The whole metaphor is based on what is the cost of owning the debt, of having it in the first place. So the point here is the message of the technical debt metaphor is not simply a measure of specific work needed to repay the debt, which, by the way, is hard enough already, but also it pushes us, reminds us it's estimation. It's the additional time and effort added to all the past work, the present work, and the future work. And remember, you can't know the future, which is why this is unknowable, that comes from having the debt in the first place. Now, I'd say don't sweat about this because it was originally intended as a metaphor to help us understand. The problem comes when you have numbers that have false meaning. It's like our engagement numbers. You need to be really careful about what it is that you're saying. So with that, we reach 0, which in this case means the impossibility for me is always finishing on time. So I apologize for going over by 2 minutes. But here we are. And if there are any kind of questions, obviously you can find me online. I'm easy to find online. At Kevlin Henney on Twitter, but you can find me on LinkedIn as well. But any questions, if there are any questions now, I'm happy to take them. Alex.
Yes, hi Kevin. I pasted the question in the chat. If you can see the private chat here in the StreamYard.
Okay, excellent. Right. So formal verification is used in hardware, but not so much in software development. What are we missing to be able to run formal verification for software development? Some language limitations, missing tools. Is anyone doing formal verification in real life software development? That's quite a few questions. Okay, let's tackle those. Reasons. So in hardware, I'm going to piss off a few hardware people. Hardware is simple. I mean, really, it is. When you look in terms of verification, what is being done, if you actually look at the main ingredients, hardware is lots of things that are identical that are replicated. That's pretty much it. VHDL, for example, is a much, much simpler language in terms of its capabilities. It is about dealing with things that are identical, and there are only a few properties that we need to verify of those. In other words, hardware is verifiable because we limited our options. The whole point of general purpose programming languages is that we don't limit our options. We do the exact opposite. So it tells us that the more limited a system is, the more likely it is that we can do certain classes of automatic verification. But we do use formal verification for certain things. If I'm using Java and I don't put a return statement into a method that, I let the control flow run off the end, the compiler will come back and say, you can't do that. You need a return here. You need to put a value because there's a path through here that will allow you to not return a value. What we've done is we've constrained the problem to such a point that it's been automated. So in other words, we do it in software, but for very limited things that our static analysis tools can pick up. It's just that software is general purpose. It's intended to do that. So that's part of the story. Another part is, yes, people do use some form of verification. It's used but it's used for certain aspects of the system. There are certain things that have been demonstrated and proven to be security safe, unhackable, not have deadlocks. In other words, again, it's this, let's rather than focus on the big picture, we focus on a very specific part of the picture that we know is provable, but we also know could be problematic, and we're able to do that. So again, it's kind of a little bit, we're kind of moving towards it, but there's still, most of the challenges comes down to meaning. The limitations of formal provability often come back to our assumptions in that case. So yeah, that's from Bogdan. Another related question. No, it was more following on from that. So yes. Any other thoughts on that one? Well, I think we're at time, Alex.
I think somebody is asking how to properly interpret concept of technical debt to company management. How to translate technical debt management.
That's it. Technical debt is the transfer mechanism. That's what it is. You know, Ward Cunningham didn't. So in other words, it's a metaphor that is designed to communicate to management. That is what it is. It's not intended for developers. It was originally intended in 1992. Ward Cunningham used it not as a general purpose metaphor. He used it because he was dealing with a financial company and he was trying to talk to them about the cost of design decisions at different points.